All right, part C. Part C says, find the rate at which the total amount of sand on the beach is changing at time t equals 4. Well, we are already prepared to do that. The rate at which the total amount of sand is changing, that's our y prime. So we really just want y prime of 4. So y prime of 4 is just going to be s of 4 minus r of 4. So we can calculate that. We can just type those in on our calculator. This is the calculator problem. And we get negative 1.908 or 9. I'm looking at the actual AP answer key instead of doing the math myself. They actually, when you round, you can actually technically round up or down. So they will accept negative 1.908 or they will accept negative 1.909. So there you have it. Y prime is going to be the same units as S and R were because we're just subtracting those functions. So it's still going to be cubic yards per hour. Now what does this mean? Well, this means that at t equals 4 hours, because this y prime value is negative. Oh goodness, I didn't mean to do that. I'm going to use my highlighter. Because there's a negative here, that means that at this time, more sand is being removed than being added, which means that it's currently decreasing. The overall amount of sand on the beach is decreasing at this time. The tide's removing more from the beach than the station pumps back into the beach. Okay, didn't ask us to interpret it, but that's what it means. All right. Last part, and this is the big one. For 0 to 6 hours, at what time t is the amount of sand on the beach a minimum? What is the minimum value? Justify your answers. Okay, so this is really where this whole idea of how we're going to end up using an indefinite integral to find a absolute extrema really comes into play, because it's asking not just for any old minimum. This really means an absolute minimum, not a relative minimum. And if you recall, back when we learned about absolute extrema in first semester, if we had the original function, just like as a normal function, if we wanted absolute extrema, we would take and calculate the first derivative and set it equal to 0, find when it is undefined, basically find the critical values. Now, we didn't do a sign chart. We didn't need to. That was for relative extrema. But we would take the critical values as well as the two endpoints of the interval, and we'd plug them back into the original f of x function to see the highest and lowest value. And we're kind of going to use that approach here, but because we don't actually have our original function as just a normal equation, the process is a little different. So, if you think about it, we started by taking the derivative. Our derivative is y prime. And we know that r prime, I'm going to stop changing colors here because it slows me down. We know what y prime is really s of t minus r of t. And we would always take our derivative and we would set it equal to 0. We'd also look for where it is undefined. So you could graph s of t minus r of t and see where it's equal to 0, or you could just graph s of t and r of t separately and see where they cross. There's different ways to do that, but you're going to have to do that on your graphing calculator and get a good window. You're only looking for between 0 and 6, and you should get that this occurs specifically at t equals 5.1179. I would encourage you, especially if you haven't been already, to be actually doing these calculations, practice doing these calculations at home on your graphing calculator as you're watching this video, especially right now. So let's make sure you can go ahead on your calculator and find out how to get that 5.1179 number. Notice I'm keeping at least one decimal more than our minimum requirement. I went out to 4 there. More than that would be great. All right, that's our only critical value. So then we would take our critical values and our endpoints and plug them into the original function. We're still going to do that now, but this is a process that is known as a candidate test. And a candidate test, we actually were doing candidate tests in the first semester, even if I didn't always call them that. A candidate test is just taking all the potential maximum values and testing them. So our candidates would be the critical values, in this case, that number right there, and our two endpoints. Our two endpoints are 0 and 6. So those are the three candidates that we have to check. Our absolute minimum amount of sand on the beach is either going to be at the start, at the end, or at this critical value in the middle. So I'm going to create a little chart here. A lot of times we create a little chart for a candidate test. And so I'm going to have t, and then I'm going to have y of t. We need to actually plug it into y of t. We're not plugging it into the derivative, we're plugging it into the original function. And if you recall, back in part B, we came up with an expression, an equation for y of t. So we're going to use that right now. It's going to be very important. So our three candidates are 0 and 6, and then also that critical number in between, which is the 5.1179 number. Now, we are going to talk about how much sand there is on the beach at each of those times. So at time 0, how much sand is there on the beach? Well, we know right here that at time 0, we have 2,500 cubic yards of sand. So that one's pretty easy. To calculate the amount of sand at 5.1179, we need to use this equation right here that we came up with in part B. So we want y of 5.1179. So we are going to take 2,500 plus the definite integral from 0 to 5.1179 of s of x minus r of x dx. So 2,500, that's the amount we started with, plus 0 to 5.1179, that's going to be the amount that has been added or subtracted in total, kind of the net amount, the net change over this time interval, and that'll give us, should equal how much we now have left. Of course, you'll need to plug all this in your graphing calculator, and you should get approximately 2,492.3694. That's how many cubic yards of sand there are at that time. To find the amount of sand at t equals 6 hours, do the same thing. 2,500 plus the integral from 0 to 6 of s of x minus r of x dx. If you do the same thing, plug it in your calculator, you should get 2,493.2766. By the way, we could have done this for the first point as well. We could have taken 2,500 plus the integral from 0 to 0, but the integral from 0 to 0 is just 0, so that's why we just started off with 2,500. Okay, so now we need to answer the question. The question says, at what time t is the amount of sand on the beach a minimum, and what is the amount of the minimum value? So here we go. So the amount, we need to write a sentence here. The amount of sand is a minimum when t equals 5.118, now I'm rounding to 3 decimal places, hours. The minimum value, or you could say the minimum amount of sand, is, well, which one's the, well, I guess we should have actually said it. I didn't make it explicitly clear, but you're comparing the three y of t values, and the smallest of those three is this one right here. So that's the minimum value, and this is the time. can be the critical value, but not always. So the minimum value is 2,492.369 cubic yards. Or you could write out the word cubic yards. So that was our minimum. All right. As you should already know, you should be working on that Unit 7 FRQ packet that you have been given over this break. If you have questions, especially about directions or what things mean, or questions over this topic in particular, it can be pretty tricky, these candidate tests and how we set up the equation for them. Anyway, any questions, feel free to email me. And I hope you have a splendid day and can find some enjoyment in your break. Bye.